I will make a plan and I will let you know. Welcome to today's lecture on proportional solenoid pilot operated two stage pressure relief valve in short form, which is called PPOPRV. First P for proportional, second P is for pilot, O is for operated, and PRV is pressure relief valve. This term is often used for such a valve. However, what we are discussing here, this is a solenoid operated, but it might be other type of drive also there. Now, this lecture essentially the continuation of the lecture 15, which we delivered maybe last time 2 weeks back. Now, first of all, again let me explain what is the valve. So, we will again I shall again explain constructional and operation features. Now, if I look into the sectional view of this valve, this is again it is a schematic, not exact section, neither it is a photographic view, this is maybe computer developed. Now, here what we find, this portion, including this portion, you can imagine this is an ordinary pressure relief valve. How it operates? This is connected to the system line. So, one side pump and other side maybe the system. Now, the flow is coming in here, not here, do not make a mistake. This is going to tank, this portion is going to tank, and this is the system line. So, here it is shown. And then the flow is coming over here and through an orifice here and a constriction here, it is going through this passage to this place. Okay. Here is another orifice. This orifice together, orifice and constriction together, we named as A, and then this is B, another orifice, and then we find the pilot stage. So, this orifice is D, this is a variable orifice and this has great role on controlling the pressure. And then after passing through this orifice, the oil which is going through this variable orifice, it is going to the tank. Okay. And in between that, which is not shown here, there is another, you can say, valve block, which is basically set the maximum pressure. When we call the proportionate solenoid pressure control valve or pressure relief valve in this case, then this is the force on pilot stage can be given by the proportional solenoid in such a way that with the input, usually voltage, it might be also current input, with the voltage the output, that means in this case pressure, will be proportionally related. Usually this operates in 0 to 10 volt, and towards the end we would say 8 to 10 volts, and towards the beginning 0 to 2 volts. It may not be linear, but in between from 2 to 8 volts the pressure relation will be linear. The advantage of this valve is that one can put easily in the control, online control. So, the in fluid power usually such phenomenon, this orifice flow, then pressure control, all such are nonlinear, highly nonlinear, but there will be nonlinear inside. However, this is designed in such a way that input output will be linear and which can be computed directly with due to this linear relations, practically no time, and due to this reason these valves are used with the modern control units or sophisticated control units, although performance may not be very close to the servo valves. Servo valve is having better performance. Considering a servo valve of equivalent size, if we say that is performing with 100%, the proportional solenoid will perform in between something 95 to 98% of the desired output, right. Now, this I have just explained or stated how it is performing, but if we look into the performance how it works, that through this orifice this passage is connected, and let us consider this is closed. Then what is happening? The oil is creating a pressure on this main spool which is supported by a spring, but this force is not enough to open this one. So, flow is being used for the system. Now, suppose there is increase in pressure, say I would start like this. The functional feature of the valve under study can be understood from the schematic diagram, and this flow, this oil is connected to here. This means that as long as there is no flow, pressure here and pressure here is constant, as well as through this orifice C. This orifice has no function with the flow, main flow, but this has a function with the damping of this main spool. It is required when there the transient due to this orifice, it dampen somewhat the motion of this, and it becomes more stable. If you remove this orifice C, still this will work, but there will be more vibration than the valve with this orifice. Anyway, the everywhere pressure remains same. So, this side of the main spool total force definitely will be more than this. So, this will remain closed. Now, when the pressure increases, then due to the thrust, it is already said we have given a force here, okay. We have given a force through the voltage. There is a proportional solenoid through this end of the spool, we can say here. So, this is giving a force in this direction. So, it is being closed and it remained closed. Now, with the pressure here, when this pressure increases, the force increases, then what will happen? This will be compressed, and this is the main spring here, this is the main spring, and this spring is an auxiliary spring just to keep this poppet in position, pilot poppet is position. This has practically no function over the force, whereas this spring is transferring the force from this to this. You may ask why it is not direct. It can be shown that if we fix this is direct, then it is very difficult to get this proportional characteristics. Anyway, so what happens? This opens, and once this opens, the flow begins from here to this drain. Okay. So, there is a separate drain connection for this passage. It also can be connected to the main passage. However, here the separate passage is function wise it is more or less same. Now, once the flow begins, then definitely there will be pressure drop through this passage. Now, with this dropped pressure here, but look at this, flow is through this passage, not through this passage yet. So, whatever pressure here, the same pressure will be there. So, but that pressure is less than this pressure. So, at one point this pressure force plus Springs force totally will be less than whatever force is generated here. So, what will happen? This will open and the main flow will go to the reservoir. Now, this situation will be maintained unless this pressure is not below the whatever force we have given here, whatever for what pressure we have given this input. Okay. Now, the question is that we could have make it is a direct proportional valve is also available. Instead of pilot stage, it is operating this one. What is the advantage of this? The advantage of this, as I told earlier, due to this pressure drops here through the different orifices, this remains stable for longer period. Why we need such stability? Look at this. If once the flow begins from here, then here is the tank pressure is almost zero pressure, or maybe a slight pressure for the filter and other things, whereas here pressure is high pressure, the system pressures. Then once the flow begins, then definitely there will be pressure drop, as well as here will be also pressure drop. By using so many orifices, what happens that here the orifice opening is very much controlled, so that maintaining the pressure almost equal to the system pressure, the flow, the whole flow is diverted to the tank. This is a large orifice, as you can see. This is also a variable orifice, but this is a large orifice. Okay. So, this is basically the operations. Now, I have shown you that by the equations how the pressure is being dropped, what the force, everything, a part of that. Today I shall discuss the rest of the portions. Now, here again if you look into this here there is a closed loop feedback. Here we are having a LVDT, that controls the armature positions for an input. This is not closed loop for the whole system. This is closed loop only for the proportional solenoid, which is displacement of this solenoid is recorded by LVDT, and through this it maintains the position with force to generate a particular force in these directions. Okay. Now, these hydraulic parts, the advantage of proportional solenoid valve is that these other hydraulic parts, including this one, this is the maximum pressure set. Again I would say, suppose this is working say at 10 voltage, let us consider maximum pressure can be controlled is 10 megapascals, or say at 8 voltage, because 8 to 10 that may not be linear, at 8 volt say 10 megapascals, or let us consider 8 megapascals. Then this valve here the setting will be slightly higher than that, so that if pressure increases above that, then this portion will not work, this directly the flow will continue like this, which including this an ordinary valve. This is an ordinary valve. So, this is additional safety feature. However, this valve can work without this one also, until there is say something wrong with the voltage input, or otherwise it would work. Suppose if the pressure increases up to 12 voltage, still this will generate only the force for 10 megapascals, and this flow will be there. But with this there will be no chance of damage at this portions. So, that is why this portion is additionally introduced there. Now, so orifice A and B are considered as the two resistors placed in series in order to achieve the required optimum pressure drop before the pilot stage. If we replace, we have done of our own experiments and we have seen if we replace one, then performance is no longer linear, neither the stability is available there. So, these are designed in considering the linearity as well as proper function. Now, what we did that instead of that block there, we put another block, just manifold you can say. So, with the hole, passage hole and keeping the passage hole intact, but this facilitated us to put the connect this one pressure gauge here to measure the pressure here, another pressure gauge here to measure the pressure here, another pressure gauge or transducer to measure the pressure here, and another to measure the pressure here, and another one to measure the pressure inside this pilot stage. However, we did not have much scope of measuring the pressure at these two points very closely. What we consider, whatever pressure is there, the same pressure is here, as well as whatever pressure we are measuring here, the same pressure is inside. That roughly, why roughly? It is almost giving the pressure drop within this variable orifice. Maybe slight error is there, but it was very close to that. So, our arrangement was like this to measure pressure at different points. Now, the primary objective of the analysis is to predict the set pressure, supply pressure. So, what we wanted to do, we wanted to study the steady state characteristics. So, for the steady state characteristics, if we know the proportional solenoid feature fully, completely, then from there if we know the orifice area, everything can be calculated and we can develop the design procedure of such a valve. However, it was very difficult to know the real solenoid characteristics, neither it was possible to test it separately, because it was an integral part. So, what we did by some trial and error, we first found out what might be the force, what are the forces generated by the armature, solenoid armature at different voltage. For that, what we could do, we measured the different orifice area, we could measure the spring stiffness, we could measure the dimension of the poppets, dimension of the solenoids, angle, etc. This data is available with the manufacturer, but the problem is that they will not provide us the data. So, we took one valve and we measured all such parameters, and then we tried to establish the design procedures, particularly to examine the steady state performance, and also we examined if we change the orifice, what orifice dimensions, then what will be the changes in the performance in the valve. Then for a given input voltage to the proportional solenoid, the flow rate through the pilot stage, that measurement we did. So, what we did, while the oil in between these passages, we put a flow meter like this, just to measure the flow through the pilot stage. All the intermediate pressures along with the pilot stage was measured by placing the transducer at different places. At steady state conditions, same amount of hydraulic fluid that enters through orifice A will pass through orifice E. So, using the orifice equations we can write down the equations, because we know the pressure at different positions. So, we can write down the equations for the flow, and we can easily, knowing the flow rate, we can easily calculate the how much drop at different places. Even say for that per pass, if we know the dimension of the orifices, even we can calculate what is the coefficient of discharge at different points. Now, the flow equations, that means we are now considering the flow from here to this, to this, to this path and here. So, first of all, first we consider the flow through this path. QD we have measured, and then we can write down these equations. This is root under the pressure difference here. This pressure we have measured, not here, we have measured the pressure here, because the dimension of this constriction could not be measured. However, there should a rho term. This rho term is included with this term. What we have considered, Ca is a coefficient, not coefficient of discharge. This, as I told, including this rho figure, this is a coefficient. This coefficient is for this orifice, and this coefficient is for this orifice. These two restrictions, say like a spring resistance in a series. So, as you know, for that purpose we can write down the equation in this way. So, we develop these equations, but this flow again equal to flow through Brie. So, we can write down this equation. The Cb also includes that rho value. I will show that how it is included. Then through the orifice D we can, this is the variable orifice. This equation definitely will be different, where Yp is the displacement of this poppet. Okay. Cp is the again the coefficient of discharge and rho part, and Pc Pd is the pressure difference between these 2 points. So, we have written in this term, but this can be detailed analysis considering the area etc. I will show that area is also there included. Now, flow through E also we can write like this. Now, here I would like to mention that orifice A and B, like the, if we say this orifice, normally we think this is a very thin plate sort of things through which there is a hole. Now, orifice may be a straight hole, or orifice usually may be in the a convergent towards the downstream. Okay. What we saw, these two are of that type. This is convergent in the downstream. Okay. And this diameter is very small, 0.5 or less. Okay. However, this orifice was slightly longer. This E is a small hole, diameter is more or less same, is slightly higher than this, but this was a long one. But as you know that for such a small orifice and such a long orifice, knowing the diameter of the hole and length ratio, we can use different formula like this. However, here still this formula can be used if we can properly evaluate that CE. Now, in all these above equations, these 4 equations I have shown, Ca, Cb and Ce for the 3 fixed orifices A, B and E respectively. These are defined in a general form as Ci is equal to Cdi Ai root over 2 by rho. So, this coefficient includes the coefficient of discharge, area of the orifice. This is the nominal area. I would say nominal area in SA, we can write this Ai is equal to the pi d square by 4, where d is the diameter of the hole without considering its geometry. Now, I is A, B, E etc. for respective orifices. Now, CDI can be evaluated from the earlier equations 4, 16, 2. If you remember the earlier equations, I think it will be 4, 15, not 16, the earlier lecture. So, this is 1 by C D square is equal to 64 L by D, where L is the length of the orifice, D is the diameter of the hole and R is the Reynolds number plus K as a constant. Okay. So, L by D ratio, the orifice varies from 1.5 to 10 normally. In this case, these two orifices was very close to that, whereas this was slightly higher, but not 10. Exact dimensions I have not shown here. K is a constant which can be evaluated from the above equations, knowing the value of C D from experiments. If we find out, we can find out the C D, then this value also can be found out. And then for a particular type of orifice, perhaps we can develop and empirical relations, so that we can calculate K any time. The coefficient C con for the constriction here after orifice A is expressed as with these relations. We put the constriction area here and 1 by K loss, we measure simply the loss there, and from which we can find out this coefficient. Okay. So, as we know the pressure drop at different point, to measure the loss over here, what we did, we removed this one and also we removed the orifice. Simply we measured the flow and pressure drop at these 2 points, and then we found out what will be the loss there. Okay. Now, from equation 21, the drain pressure P D can be readily evaluated in the written line, and pressure P R is also known. This pressure also measured, so this is known. So, with such the known values, we can calculate the initially what we did, we evaluated all coefficient of discharge. Whenever a orifice is put, we first evaluated the coefficient of discharge of all such points. Now, this PR is not very high, it is 0.05 to 0.8 megapascal only. That of course depends on how much restriction you have put in the written line. If there is one filter only, then maybe one value. If filter with say cooler is there, then it will be more. This depends on the resistance, which easily can be measured. For the evaluation of the PC, PA and PS from equation 21, the pilot poppet displacement has to be determined first. Now, you see this first we have measured the pressure, and next we have found out the CD, and from which we have prepared the set of equations. Now, what can be done with those, using those equations, again we can PC, PA, PS, all we can, PS is known value, all we can calculate with respect to this displacement, YP displacement. Say for example, this means that next for the next calculation, we need to calculate the Y P, how much will be the displacement. Ultimately, we have to put in terms of the displacement all the equations. Okay. So, in order to find Y P, that is the pilot poppet spool displacement, PC and PD is replaced by the pilot stage force balance equations So, this equation 14, if you remember, this 14 equation was used in terms of QD and YP obtained from the equation 21. So, first we calculated CDN etc., then we from knowing the QD we calculated YP. I will show these equations. Now, we should recall here what is the geometry for this poppet spool or the orifice area. If you remember, in the earlier lecture I described that how the flow is occurring here. The flow is coming over here and then this flow is going like this and it is ultimately going to the tank through this orifice E and the leakage passage. Now, the we know this angle, okay. We know this whole diameter. So, area must be this annular passage that which we can calculate from this. I mean, it is not like that we are subtracting this area from this area, rather we are considering the perpendicular path through which the leakage is going. So, we have taken this component. Pi dp is the peripheral area, dp is the diameter of this hole and phi p is the angle. Okay. So, we use this equation to estimate the area. Now, here another point is there. What is the jet angle here? In normal course we can expect jet angle will be phi p, but in real case it is slightly higher than that. That means there is a separation of the flow here. So, flow you can say that it might be slightly higher than this. So, actually we should take that angle here, but there is no way we can measure this angle. So, what we do, we take this angle, later we put a correction factor knowing experimentally what is the flow actually occurring there. Okay. Then with further derivation, equation 14 is transformed into a third order polynomial equation for yp and is expressed as, I am not showing the details of these equations. From the note you can, or if you just go back to the earlier lecture, from there you can calculate and ultimately we can put this equation in this form. This is the third order polynomial equations where E can be put K, SP and Cp and B is put within these terms. These are coefficients, these are all coefficients where this is the force, driving force, and C is Cvp, then neta q d3 by 2 pi dp by rho sin 2 theta p. So, these derivations again I am not showing here, these derivations can be obtained once we exercise these equations, then automatically these terms will come and which are put in this form, and d is equal to minus ap into qd. AP is the area of this, I mean this hole, not this orifice here. AP is the this whole diameter, which is a known factor. QD is also known. Now, as in equation YP, equation 24, clearly there will be 3 roots. One of that will be positive and real, and which can be considered as pilot poppet displacement. Okay. So, if we solve these equations, then we will have 3 values, one of that which is positive and real, we will consider that value for the poppet displacement. Okay. So, combining equation 21 to 24, the different pressure are finally expressed as this PC, the pressure here is equal to PB. That means PC and PB, this zone pressure is derived by QD is the drain flow divided by Cp Yp square plus Pd. Okay. Then Cp we have evaluated earlier, Yp we are calculating from these equations, these solutions, and then clearly we can calculate the pressure there, and Pa is Qd by Cb square plus Pb, and Ps is Qd square by 1 by C square plus 1 by C cot square plus Pa. This all the equations written from the earlier we wrote the equations, and this just we have written this equation in terms of pressure. So, this easily can be evaluated, and after that the variation of all the forces involved in the force bearing equations with the common voltage for the pilot stage illustrated here, which we can derive. Okay. This force equations earlier we have shown, equation 14, this earlier lecture we have shown. Now, here we have plotted. Now, if you look into this figure, now here system flow is this much Qs, that was the system flow, and for that F dr F, this is F dr, these are different forces. F dr is the force form for solenoid, Fsp is the spring force, Fps is the flow force. Am I clear? F dr is the force generated by the armature, I mean that solenoid, proportional solenoid. Fsp is the main spring force, not this one. There is a spring this side. This is not the main spring is here. So, that force, okay. And then Fps is the flow force here, and Fprp is the force generated by the pressure here. Okay. So, these are plotted. So, this will be the nature of the forces here. Now, individual forces are evaluated analytically from their respective equations, this which we have done earlier. It is observed that throughout the entire operating range, the pressure force Fprp largely follows the driving force F dr. This is the driving force. Okay. The spring force remains nearly constant in between the spring force after some initial increment. Okay. So, this means that at the say for example, when the valve is being operated, maybe the voltage input 4 to 7 or 8, rather here the linear portion is 2 to 8 for this valve. So, for voltage input from 2 to 8, what you will find, this spring almost acting as a solid bar, and the armature force is being balanced by the pressure force and flow force. Again I will repeat that why we need that spring. If we give that direct force directly by this pole, there will be nonlinearity. This nonlinearity will be reduced if we use a spring in between that. The flow force is found to be increasing with the increase in common voltage. Obviously, if the force is increased, then what will happen? There is a much pressure drop. With much pressure drop, there is the increase in flow rate. So, there will be increase in the flow force. However, the magnitude of flow force is negligibly small in comparison with the other forces. This is again that although this force is increasing flow force, but still it is less than the other forces. Unlike the pilot stage, in the main stage the flow force has a significant role on the steady state force balance of the poppet. Now, here what we are showing, this is the main poppet we are showing. If you recall the valve configurations, this is the main flow through which the main flow is going to drain in case of relief. Okay. So, in this case the flow force has significant role. The main reason is that quantity of flow is much higher here, and definitely as I told, for the balance, for the longer stability, this valve is designed. This means that this orifice area is very small, so that there is enough pressure drop to maintain the system pressure close to the system. Say in case of direct valve, what happens? Once this poppet opens, the pressure drops inside, then again it closes and again it opens. So, there will be chattering sound. But in case of this balanced piston, I mean pilot operated valve, what is called two stage valve, this remains balanced for longer time. So, that is why there will be the less orifice area, much flow, and due to that here will be the high flow forces. Okay. Now, here the flow force for different input conditions are evaluated using the expression 12. Here the equation 12 I am not showing, you should compare with the earlier lecture, and this is according to the equations 12, whereas the from the equations, the other equations, there is equation 18, we get a different value. One is the equations we developed from the general equations, another with respect to the valve in terms of force and other things. So, why this difference is there? Definitely, as I told, we could not consider all the parameter inside. So, there will be some differences. Now, these differences are observed in all cases who have analyzed such valve, and therefore, we need to evaluate the equations considering a factor for these corrections, which we called correction factors. So, the flow forces obtained from two approaches are clearly illustrated in the both the figures, earlier figures and these figures also. And then the inequality essentially demands for a correction factor, which should be introduced in the expression of flow force. Now, we will look for that one. Now, the modified equations of flow force is then can be written as, with a factor, we have these equations again we have rewritten, and here we have, earlier we developed these equations without this one. If you remember this equation we developed earlier, where we did not have this one. Okay. Now, we have to calculate this one, this kappa, this factor, this is the correction factor. Now, where k, the correction factor, k or kappa, whatever you call it, I think we used kappa. The correction factor is the ratio of flow force obtained from equation 18 to the ideal flow force given by equation 12. 12 gives the ideal flow and 18 gives the obtained flow from these geometries and other things. That means 18 equation without this kappa was there. Okay. Now, in some previous investigations, this in the reference, earlier reference we have given, today I also give the references. These say Davies, it is 1994, this is 1998, this is even 2002. They faced similar problem, and we carried out such analysis in the year of 2004, 2004, and this time when we had to face this problem, we found they also faced similar problem, but their valve was different. So, we had to evaluate this value of our own. As shown in figure 8, the factor K is not constant, but is found to be varying with the supply pressure. This is not the figure 8, the earlier figure 8, this kappa value is not constant and found to be varying with supply pressure. So, measuring the supply pressure, we can find out these values. Now, to find out these, what first of all we should know what is the angle, this poppet angle here. So, knowing this poppet angle, due to the typical poppet configuration, the flow angle may not be same as the half poppet angle for all the input conditions. I mean, here again this we wanted to mean that jet angle is not always matching with the phi s. So, due to that this correction factor is required. The actual flow angle seems to be larger than this geometric angle of the poppet. Large flow angle enhance the flow force. The assumption of uniform pressure distribution on the external poppet surface may not be applicable here. The characteristics of the flow force correction factor may be used as a reference for the sensitivity analysis of the valve. Okay. So, this not only this correction factor, from the correction factor again we can examine the sensitivity of the valve. What is sensitivity? That changing the parameter like a spring constant and other value, what will be the change in the flow or pressure, etc. An attempt has been made to calculate the armature displacement. So, if we think in terms of design of such valve, so now we need to consider what is the armature displacement. Without the details of the constructional and functional features of the solenoid, the displacement is predicted from the geometric details of the pilot stage and the developed driving force model. You see, as I told that it was very difficult to measure the displacement. Of course, if we can calibrate, if you could calibrate the LVDT and if you could take the output from LVDT, then it could be possible to measure the displacement. But whatever the information we already have, we have the geometric relation inside, we have the spring stiffness, we have the flow, and from there we can find out what will be the displacement, and from that equations definitely it is possible to find out the armature displacement and what we established, and with that armature displacement we again re-examined for different pressure setting, and we found that result was correct. So, we consider that is the armature displacement, and ultimately we developed all the equation in terms of armature displacement also. Now, here this first of all, to do that what we measured, that we measured this length. Okay. So, this is a fixed geometric length, and then say this is the, say this point is touching over here when it is 0 positions. So, what we measured, the LP we measured from the top to this positions. That means, if we measure this distance, that is LP was when LP was 0. Okay. Now, this is, you can say, this is the opening from the orifice point, and then this is the position of this seat, I mean this step, and here also this step. These two are some fixed dimensions, and then this is the dimension for the compressed spring, which we, the free length F LP is the free length of the spring minus this displacement, and here again we had to measure this cap dimensions, because the spring was sitting from here to here only. So, this dimension we had to include, and then by equating we were calculating the displacement of the armature. So, here the critical values are these, because what is the compressed length of this spring, and to find out this armature length, and we had to consider this length also. So, these are all fixed lengths, geometric. So, this will not vary, but once with the force this will vary, this will vary, and this will vary. Okay. Now, next the equation, the armature displacement can be written in this form. I am not going into the details. Knowing these dimensions, you can easily find out. Say this is the LIO, this is the LP. Okay. Now, it is not exactly matching this, I mean because this is written in maybe one format, this is other format, but these are corresponds to this. So, LC is here, these dimensions, LL is this one, LB is this one. Okay. So, you will be able to understand why if this figure is enlarged. I think you cannot read it, but there is slightly mismatch. Anyway, this is this dimension which can be estimated. This is the fixed, this is also fixed dimensions, this LC is also fixed dimensions, this is also we have to measure. Now, where the poppet displacement YP and the pilot main spring compression YHSP, this one YP is evaluated from the analytical model we have already developed. Now, the driving force is transmitted to the poppet through the pilot main spring. Therefore, YHSP is found from the equation of the spring written as YHSP F dr, this is the driving force of the armature, divided by KHP is a, we can say, this spring constant of the main spring. Now, this is again, you can see, are evaluated all three displacement involved, this armature, this and this in the pilot stage are plotted against the current. So, if we have now plotted these three characteristics, now this one is the YHSP, that is the spring, compressed spring length, okay, displacement of the spring, and YP is the displacement of the main spool, and Y armature is the displacement of the armature. Now, if we look into study this curve, this is, as you can see, this linear, and this is also we are getting linear, whereas this YP is not linear with the displacement and current. Obviously, when current is less, then displacement will be much higher. This is obvious. You see, this current is less means the load is less, and that load definitely this less pressure drop. So, there will be more displacement. it can be seen that the armature displacement becomes linear after some initial nonlinear region. Okay. At smaller current range suggesting presence of inherent nonlinearity within this valve. You can say this is in terms of current we have written, because ultimately in the armature what is fed, that is the current. Our input is voltage that converted into current, and that current relations we find nonlinearities here, as well as there will be some nonlinearities here also. So, from this to this you can say linear, and this is we normally keep the operating zone from this to this. That means, about when the current is 0.7 to 1.6, it corresponds to roughly 2 voltage to 8 volts. So, now as you see this from this point of view, we need to modify this our equations for in the usual form, and what we find, considering that the armature position for different input currents for different driving force, that is for the different driving force, is independent of pilot's mainspring stiffness. So, definitely we can examine if we change the spring stiffness, what will happen. Definitely the range of voltage might be, it will change, but performance may not change very much. As I told, after an initial compression, the spring almost acts as a solid bar. Consequently, the pilot poppet displacement may be expressed in terms of driving force, pilot mainspring stiffness, and the armature displacement. So, modifying equation 27, now the expression we can write in this form. Here directly we have the spring stiffness which we have measured, and the force also we can estimate from our input voltage and others, and we can calculate. So, with this we have this part we have replaced, this one we have replaced by this force. Okay. So, now Yp can be calculated, and in the analysis the pilot flow rate is no longer an input. It is not an input, our input is the voltage, we can say it is an unknown quantity and is to be determined from the analysis. Say in fact, Yp now we have to estimate for the performance. The pressure drop across the pilot stage is to be evaluated before the evaluation of the pilot flow rate. From the force balance equations for the pilot stage, the pressure drop may be evaluated as, now we can write down these equations. This AP is this orifice area, AFS is this ring area, and we can calculate PC minus PD knowing these two force. So, now we have to finish very quickly. So, I would like to say that from the pilot stage force characteristics, the pilot stage flow force is found to be negligibly small in comparison to the other forces. Instead of using equation 3 for the flow force, it is quite reasonable to express it in terms of pilot poppet displacement and pressure drop, assuming constant coefficient CdP and CVP, the final form of the above equation now written in this form, whereas the CdP and CVP is the two coefficient of discharge at these points. So, these are separately evaluated and we can now write down these equations. Once the pilot poppet displacement and the pressure drop are evaluated, the pilot flow rate can be found directly from equation 14. The individual pressure are then evaluated using the equation 21 to 25, and here we have seen the 3 different plot. Okay. The analytical results, what we have done, actually we have estimated what will be the sensitivity. The analytical results is plus minus 5% change in the pilot spring stiffness. This is purely theoretical analysis. What we have developed with that, what we have shown here, you can see the change in pressure and this common voltage. This is 100% means the original spring, and if we increase this stiffness by 5%, then it is this one, and if we reduce the stiffness by this one, we will get this is the curve. This means that by simply changing this spring, we will have different pressure range for different voltage, but the nature of curve is more or less same. Let us examine the other also, that what will be the changes in QD. What we find here for the our original spring, this is more or less constant, linear, whereas due to these two changes, what we find, it is becoming highly nonlinear. Okay. So, and also if we look into the flow force correction factor, we find that these two are also different from the linearity, and then obviously if we want to use, say for example, this is 5% less, we have to be very careful. Probably this design will not be feasible, whereas by increasing the spring stiffness the 5%, we can still use this. So, this is with this I would say that I wanted to show that how a proportional valve can be analyzed for its steady state performance. We have not yet shown what is the transient performance. Okay. Now, I think you can understand this from the self study, and there is of course the conclusion part, which I am not going into details because you have to read it, but I have discussed throughout these presentations what might be the conclusions, and finally these are the main source from where we have developed. I have developed these lectures, including our own research, and thank you for listening.